Hello guys, I would like to continue our discussion and continue to solve more problems from chapter 14. And we all know that the purpose of this chapter is to introduce us to the relationship that the work, of all external forces applied on an object is going to always be equal. Let me do something here. The work of all external forces will always be equal to the change in the kinetic energy of the system, right? So work of all forces, all external forces, right? So here external forces has to be equal to the change in the kinetic energy of the system, which is always equal to 1 over 2 m, and sometimes you could have multiple masses and you have to incorporate that as we did in the final example, in the previous example, minus 1 over 2 m vi squared. If you have multiple masses, then you basically have to incorporate a summation on the sky. All right, what I'd like to do is I'm going to solve this first problem that we have here. Basically, we have a cyclist who is pedaling at A, and at A, he is moving with a 4 meters per second. So his velocity is, so I'm going to draw that very quickly here. So we have a pedalist at point A right here at the horizontal. He's actually moving with 4 meters per second. And by the way, this is not a free body diagram. We never put velocities, right, on a free body diagram here, just a diagram to show you guys what's going on. And then he stops actually pedaling here and would like to see how high he actually goes up on that curve. So he goes up for some height h here, and we would like to also find out what is a normal force when he actually stops at that particular point, which we don't actually know yet, but we do know the equation of this curve. So the path is actually already provided to us as x square root of x plus square root of y is equal to 2. All right. So, and we're also going to neglect friction. So how do we do that? How are we going to find that elevation? So here's what we're going to do. We're going to do exactly, we're going to apply this equation, right? Well, when I do the work of external forces, I have to first identify what are the forces, right? So if the bicycle is, if the cyclist is here, so I'm actually going to kind of like draw it very quickly. You know, this is a bike, it's up, right? And this guy is like that, like this, like that, like that. This is a cyclist. I think we're missing a bar. Here we go. Okay, so if the cyclist is here, what are the forces that are being applied on the bicycle? Well, we're neglecting friction, so we know here we only have normal force. And by the way, here we're treating the bicycle as a point mass, right? We're not treating the bicycle as a whole, you know, several rigid bodies. We have a weight applied at the center of gravity, and anything else on here? We may have friction, but friction is not going to be included, right? So what is the work of all the forces? So, you know, so it's going to work of normal force plus the work of gravity has to be equal to the, so find the kinetic energy minus the kinetic energy, and we need to find out how high he reaches before he comes to a stop. So if he comes to a stop, then your final kinetic energy is going to be 0. So this guy is going to be equal to how much? Simply minus 1 over 2 m v0 squared. Okay, well, what is the work of the normal force applied on this object? Normal force is always perpendicular to the motion, and we know the work of any force is equal to F times ds. So this is that product between the force and the motion. We know now the motion, like ds now is here, right? This is your ds. We know n is perpendicular to that. The angle between F and ds is 90. Therefore, F times ds is 0. So the whole work will be 0, right? It never does any work. Now, what is the work for gravity? Well, we said the work of gravity is really independent of the motion. Ultimately, it will simply depend on the elevation. So if you started here and went up by a distance h, how much work have you done? So it's going to be simply minus mg times h. is going to be equal to minus 1 over 2 m v0 squared. So the m and the m will actually cancel out. So here we can multiply by minus to make this whole thing positive. So v0, or I'm sorry, h is going to be equal to v0 squared over 2g. Here we go. So now we just calculated our h. Second step is we need to find the normal force at that point. But how do we find out that point here? So here's somewhere here, right? How do I know that point? I need to know its x. How do I know its x value? Well, also, in order for us to be able to find the normal force, we have to actually find the angle, right, of the normal force that the normal makes with gravity, right? So let's say this is a slope. Well, I can actually find that angle here, right? I can find that angle by looking into dy over dx, right? And if that angle is theta, this guy is pi over 2 minus theta, right? And then this whole thing is 90. Then this guy here actually has to be also equal to theta, right? So basically what I need to do is I need to find x, right? And from x, I can use the slope to find theta. And when I find theta, basically I can sum the forces in the vertical direction and I can find m. Do I have any other values on acceleration diagrams? Like this is the force diagram, right? On the acceleration diagram, do we have any acceleration? Well, we'd have to plot it. But let's first find x. I'm gonna find x based on this relationship. Okay. Well, I have x 1/2 plus y. So y, I'm gonna actually solve it for this h, right? So this is gonna be square root of v0 squared divided by 2g is equal to 2. So x is gonna be equal to 2 minus square root of v0 squared over 2g. So this is x 1/2. So I'm gonna actually square this whole thing up. And there we go. Okay, so this is x, and I'm gonna actually call this point x1. Not gonna do the actual computation, but I'll let you guys do this. So there's no problem here. So this is simply square root of v0 squared, so we can actually find x. Now, how do I find the slope, or how do I find the angle theta that the bicycle makes with the horizontal? Then I'm actually gonna use this relationship again, right? Well, I know tangent theta will be equal to dy over dx, and if tangent theta is positive, or if dy over dx is positive, it means that the curve basically makes a positive slope with the curve, right? So if theta is positive, it means that the curve is actually going like this, right? And if the curve is like that, then theta is negative, right? This is a curve. If dy over dx is negative, then we know theta is going to be downward. Right, so here obviously we know it's going to be negative. So how do I find dy over dx? Well, let's actually start from, so we have x 1/2 plus y 1/2 is equal to 2. If I want to I can simply differentiate that. It's going to be 1 over 2 x minus half dx plus 1 over 2 y minus 1/2 dy is equal to 0, right? So 1/2 and 1/2 will actually cancel out. I can y minus 1/2 dy is equal to minus x minus half dx. You can divide this whole thing by dx. So dy over dx is equal to minus x 1/2. If I want to move y minus half to here, you know it's going to be y half. If I put it here, I can also do it like that, correct? So just move it like that. So it's going to be minus square root of x over y. Okay, and the minus simply indicates that the curve is actually going downward as you move from left to right. So dy over dx is equal to minus x, which we have its value. What is the value for x? Is equal to 2 minus square root of 0 squared over 2g squared over y, which is 0 squared over to G. Once we do this, we can actually plug that in, and then we can find the individual values that we actually have going on here. And I might as well just do this for you guys. So do it here. So we said H is equal to V0 square over 2G. What is V0 square? 4, right? So it's 16 over 2 times 9.8. Let's quickly compute that. 16 divided by 2 times 9.8. This return a value of 16 meters. So this is my elevation. Now as my x is gonna be equal to the square root of 2 minus square root of 16 divided by 2 times 9.8. Let's calculate this. So we have square root of 16 over 2 times 48, which is actually h, right? Well, if you do this whole thing, then you end up with 1.04 meters. And back to d over dx, it's going to be equal to minus minus, we said what? X over y, right? This is our value. So minus, what was our x? 1.04 divided by y, which is 0.81. And if we do that, square root of 1.04 divide that by 0.81. It's actually 1.13, and that is equal inverse tangent, right? Of minus 1.13, which is equal to 0.84 radian. It's going to be 48. Okay, so that is actually going to be equal to minus 48.1 degrees. So you can also verify these computations. So this is what we have here. So this is our theta. So now let's come back to our free body diagram. So the bicycle is here. This is your normal force. This is a horizontal. This is your curve. And I know my curve basically makes this angle of 48.1 degrees. So I'm removing the minus because now I know the angle is going to be in that direction. Basically, it's being made from the horizontal to the curve in that direction. And I know gravity will actually be like that. Now, how about the acceleration? Do you think we're going to have any accelerations? So let's replicate the same diagram here. Do we actually have any accelerations? Well, we actually do we have any accelerations? Do we have any AN? Right. So this is my curve here. Right. Do we have any AN in the normal direction? Well, if we actually had AN, it would be equal to what? M v squared over radius of curvature. And you notice I didn't calculate the radius of curvature because I know when a cyclist actually, like that, when cyclists go up, right, it's going to have a velocity here is equal to 0. So this guy is actually 0. So there's no need to actually calculate this guy. But how about this guy? Do we actually have a tangential acceleration? AT, and I believe we'll actually do. Why? Because there's a component of that force is actually acting in this direction, right? So this component of the force is actually going to give you AT, right? But if you actually were to calculate N, then, you know, we don't need to calculate AT. Here, tangential acceleration simply means that, you know, if the cycle is actually going up and then he you know, instantly stops, then, you know, the next moment he will actually move backward, right? Meaning that he has an acceleration, or the velocity will actually has a tendency to actually go backward. That is why you have a negative acceleration. Okay, and then these forces have to basically balance these inertial forces have to balance these external forces. Okay, let's calculate N. So what I'll do is I'm going to sum the forces along the normal direction, and what I'm going to end up with is N. Okay, we said this angle is 48 degrees, and this angle is 90 minus 48 degrees, and this also is that. So this guy also is 48.1 degrees. Okay, make sure that your geometry is good, right? By solving all these problems, basically, you can actually learn all these geometries as well. So summing the force along N is going to be N minus mg cosine 48.1 degree is equal to 0. So therefore, my normal force is going to be equal to mg cosine 48.1 degree. And there you go. This is your normal force. Okay, guys, so this is that example. Let's continue over and work on this problem. Okay, problem 14.1. And what we have here is that you have a 75 kilogram crate, which starts from rest at A, and it actually reaches a velocity of 6 meters per second when it passes through point B. What is actually happening during the motion? We have a force F that is being applied on this crate, and the force is constant, and we actually need to find the value of that force. What we'll do is how are we going to solve this problem? So we're going to apply the same concept. We're going to use work and energy, okay? And well, let's start by doing a free body diagram on that. So what is a free body diagram? Why do I need a free body diagram? Because I know work of external forces is equal to delta KE. So how do I know the work of external forces if I don't know the external forces? So I do a free body diagram to identify the external forces, and then I will do that. Okay, what are the forces that are being applied on here? We have N, we have mg. Well, we would have friction, but they told us to basically neglect the friction. And we actually have a force, a variable force F that is being applied on this object. What is a change in kinetic energy? Well, it starts from rest, right? So this guy is going to be 1 over 2 m final velocity minus 1 over 2 m b0 square, right? Final velocity here is have a value, but b0 is 0. So work of all the external forces has to be actually equal to 1 over 2 m vf squared. And we actually know that the final velocity here is going to be equal to 6 meters per second. Okay, what else is going on here? Well, we need to find the work of all the external forces. So we're gonna list them up. So the work of the normal force plus work of gravity plus work of F has to be equal to 1 over 2 mvf squared. What is the work of the normal force? I think it's going to be 0 because normal force is not lifting, it's not moving this object forward, right? How about the work of gravity? Also it's 0, right? Because this guy is moving in horizontal plane, so we only have the work of the force F. How am I going to be able to find the work of the force F? Well, this is what is happening, right? Let me just do this very quickly like this. So this is our system here, and we start at A and we end up at B. And if you actually plot this at any instant, right, then my force is going to be in that direction, and I'm actually making an angle theta, but that angle theta is actually changing. So initially theta is here, finally is here, and then at the end theta is going to be here, right? But what is x? So I'm going to actually define x to be this guy, right? X is how much you have actually traveled, and now I know the work of the force F is going to be equal to how much? F as a vector times dx as a vector right? So it starts at 0 and it ends at P. So it traveled basically by a distance of 6 meters, right? But this is the dot product between F and dx, and I know dx is going to be in that direction, right? Elementary dx. So F times dx is actually nothing but 0 to 6 F times cosine theta, right? So basically you are projecting the force F on this axis, right? Or we have the dot product F times dx will return F times dx as magnitude times the angle times cosine of the angle between these two vectors, which is theta, times dx. Well, now the problem is if you want to integrate this guy, cosine theta is actually variable, right? So I can actually look into this geometry and then actually I can get that because I know this distance right here is how much? 6, right? And I know cosine of an angle is equal to adjacent over hypotenuse, right? So what is that distance, right? At any value. So if you are at x, what is this guy? This guy will actually be equal to this whole distance, which is 6. Well, we know this whole distance is going to be 8. So you've moved how much? 8 minus x, right? If you moved x, then the remaining distance is going to be 8 minus x. So then you can check out the diagram. So I have 8 minus x here, and then I have 6. So I know that this guy is going to be equal to what? Square root of 6 squared plus 8 minus x squared, right? So the cable that is the length of this cable. Okay, so what is that integration going to be equal to? So I'm going to actually continue it here. So we said the work of the force F is going to be equal to F times cosine theta dx, and we go from 0 to x, and we said at any instant when you have an angle theta, the remaining distance is going to be, after you have moved by a distance x, will be 8 minus x, and we know this distance right here will never change. So this guy is going to be equal to square root by Pythagorean 6 squared plus 8 minus x squared. So now basically we are converting cosine theta into dx because we have two different variables here, theta and then x. So we cannot integrate that. So now what is your cosine theta? Cosine theta is equal to this guy over this guy, right? So 8 minus x divided by 6 squared plus 8 minus x squared. Okay, so I'm going to replace whatever value that I have. So now I have cosine theta in terms of x. So the work of the force F is going to be equal to 0 to 6. And then I know F is constant, so I'm going to put F here as magnitude is constant. So cosine theta is equal to 8 minus x, divide that by 6 squared plus 8 minus x squared, and then dx. Okay, so those few who are math savvy, they will recognize that I can actually put this guy, make this guy to be equal to v squared, right? And then if I do dv, I'm gonna actually end up with minus 8 minus x dx, right? So if you actually let v squared to be equal to 6 squared plus 8 minus x squared, right? I can do replacement of variable in this integration to be able to integrate that. So if I actually differentiate this guy, I end up with what? 2 dv, 2v dv, right? 2v dv. If I differentiate this guy, what am I going to end up with? So 2 8 minus x minus dx, right? Multiplied by minus dx. Okay, so if I make this variable, what do I end up with? So I can now start doing some replacements. So 8 minus x multiplied by 8 minus x multiplied by dx. Well, 2 and 2 will cancel out, right? 8 minus x dx is going to be equal to how much? Minus v dv, right? Okay, so this is the top, and then at the bottom I have square root of 6 squared plus 8 minus x squared is actually equal to what? Square root of v squared, which is actually equal to nothing but v, right? So the bottom is equal to v and the top is equal to how much? Minus v dv. And how about the variable? When x is equal to 0, what is v equal to? So v squared is going to be equal to 6 squared plus 8 squared, right? So v is going to be equal to square root of 6 squared plus 8 squared. And when x is at the end, what is your v? your V is going to be equal to, or V squared is going to be equal to 6 squared plus 8 minus 6 squared, which is equal to how much? 2 squared, right? So your V is equal to square root of 6 squared plus 2 squared. Okay, so what is your work of the force F? So the work of the force F is going to be equal to F, the magnitude of F as a constant. So the boundaries, I have 0 at the bottom. So 0 at the bottom, V is equal to square root of this guy, square root of 6 squared. I'm gonna just keep that for a second. You can do the computation in a bit. And then when X is equal to 6, then I'm gonna be here, 6 squared plus 2 squared. And 8 minus X dx is equal to what? Minus VdV divided by 1, divided by V, right? So that's it. So V and V will actually cancel out. So it simply ends up with minus dV. So we know we can basically switch these guys. So F dV, so at the bottom I'm going to be 6 squared plus 2 squared, and on top I'm going to be 6 squared plus 8 squared. So the work of the force F is going to be equal to F square root of 6 squared plus 8 squared minus square root of 6 squared plus 2 squared. And I know the work of this force is going to be equal to how much? Minus 1 over 2 m, which is 75, multiplied by the velocity squared, 6 squared. So here you go. So we can actually find the value of our force, which is equal to 1/2 75 6 squared divided by square root of 6 squared plus 8 squared minus square root of plus 2 squared. But you guys do the rest here. This force has to be in newtons. Okay, guys, so that is that problem. Okay, guys, so that is it for the session. For the next session, we're going to start looking into power and efficiency. And I'm going to be posting the session actually pretty shortly on that. Okay, guys, make sure you continue to solve problems and assignments on time. Make sure you accompany me in all the sessions that I'm doing, and you know, don't lag behind and then, you know, leave lectures that you don't watch until the exam. So make sure you keep on solving these problems.